All right, I want to just do a walkthrough from Lewis dot structures to VSEPR diagrams, show you some models, and make sure everybody has clarification on the symbolism in the VSEPR drawings, what they mean, so that when we get into the polarity lab and polarity discussion Monday, Tuesday, and Wednesday of the first week of February, we will be all on the same page. So with that being said, this key is up online. It's been there since last week. Just want to go through the whole process for a couple of these, show you the different families of VSEPR shapes, and then I will always reply to any follow-up questions that you have. To send it to me on email. So the first one on this sheet is carbon tetrafluoride, CF4. The carbon is going to give us 4 valence electrons because it's in group 14. 4 valence. Each fluorine in group 17 is going to give us 7. Since we have 4 of those, we have 28 total. 4 and 28 give us 32 valence electrons to build this thing with. Carbon has 4 bonding sites. Each fluorine only has 1. So we're going to put carbon in the middle. We're going to single bond it to each fluorine, so that's a single shared pair of electrons between those 2 atoms. And then each fluorine is going to have 3 lone pairs or unshared pairs around it. And that gives us 8, 16, 24, 32 electrons total. That also then gives us a full octet or a full outer shell for all 5 atoms that are in this structure. Remember, anything that has less than 4 valence electrons, anything that has less than 4 valence electrons simply wants to make a bond and pair up its unpaired electrons. So hydrogen has 1 unpaired electron. It wants to make 1 bond. Something like beryllium that rarely but does make covalent bonds. It has 2 unpaired electrons. It'll make 2 bonds and be content. And then something like boron or aluminum that occasionally will make a covalent bond. They are going to make 3 bonds, and then that's it. Okay. Carbon has 4, and then anything with 4 or more wants the octet. Anything with less than 4 valence simply wants to bond its unpaired electrons. When we go from the Lewis dot structure to the VSEPR drawing, we need to figure out what shape we're going to have. And we use the ABE formula for that. Remember, A is the central atom, B is the number of atoms bonded. 4 atoms are bonded in this case, AB4, and there's no lone pairs on the carbon. So that gives us this shape called the tetrahedral. And the thing I want you to notice about the tetrahedral is that you have 3 dimensions. Okay? You've got this carbon that is standing up out of the center. Sorry, this hydrogen, carbon, so actually fluorine, carbon, fluorine. These 3 are all in the same plane. So we draw those with a regular line. That just means that it's in the plane of the paper. Okay? And then we use 2 other symbols, a dashed line for the element that's going back away from you into the paper, and the wedge that is coming out of the paper at you. So we have to be in 3 dimensions to spread 4 items out as far as possible. That gives us the tetrahedral, and this is how we would draw that tetrahedral. These 3 atoms are in the plane of the paper. Okay? They're flat with the paper. This dashed line, that's going back into the paper. This wedged one is coming out at you. Okay? If we look at H2SE, 2 hydrogens, each one gives us a single valence electron. We have a total of 2. Selenium gives us 6 valence. That's a total of 8. Selenium is going to go in the middle. and the reason it's going to go in the middle is because it has two bonding sites, two unpaired electrons, where the hydrogen only has one. Okay? So the element with the more bonding sites and the lower electronegativity goes in the middle. That's selenium. Bond your hydrogens, fill in the octet, fill in the outer shell with lone pairs, and we're good. In this case, you have A, B2, E2. So we count the pairs of electrons on that central atom. A, B2, E2, if you look at your table, is a tetrahedral family, but it has lone pairs of electrons on it. It has lone pairs of electrons on it at the top. So it still has 4 domains, or an electron domain is anything that is attached to a central atom, whether that's an electron pair or an atom. So when we go to draw this, we just focus on what we can see, which are the atoms. The electron pairs can just get dots up top. Could you put the wedge in the dashed line? You could. It's a little more complicated than it needs to be. I wouldn't necessarily take the time to do that. Third one on the front page here is a third shape, which also happens to be a tetrahedral shape. The nitrogen gives us 5 valence. Each iodine gives us 7. So 3 7s give us 21. We're at 26 electrons total. Nitrogen's going to go in the middle, and that's because it has 3 bonding sites compared to iodine's 1 bonding site. It has 7 valence electrons. It has 1 unpaired electron. Nitrogen has 1, 2, 3 unpaired electrons. The one with the more bonding sites is going to go in the middle. So what we end up with is a lone pair on top. That's going to give us an E. 3 bonded atoms, B3, to that central atom. So A, B3E, that's triangular pyramidal. That again is a tetrahedral shape, but instead of 4 elements, we have 3 elements in a lone pair. So the base of our 2 compounds here, if we take a look at our CF4, you can see through the equatorial line right between there, splitting it in half, you have a single, a wedge, and a dash. Look down here at this tetrahedral family. You have a regular bond, a wedge, and a dash. So the bottoms of the tetrahedral and the triangular pyramidal are identical. Okay? Again, that's a 3-dimensional shape, triangular base. It's popped up in the middle, and the reason it's popped up in the middle is because this pair of electrons repels the bonded electrons down away from it. So you have your A, B, 3E. You're going to need a regular bond line for the one that's in the plane of the paper, dashed line for the one that goes back, and the wedge for the one that comes out. On the next page, you're going to see the top 2 are going to be AB4 tetrahedrals. When we get into oxygen and nitrogen, because of how they are connected to one another, and you can actually see this very easily if you do the jigsaw method of making the Lewis dot structure. If we take an oxygen and we put its electrons, its Lewis dots, and we take another oxygen and we put its Lewis dot, you can see how those unpaired electrons can connect to make a double bond. And that would give us 2, 4, 6, 8 electrons for that oxygen, 2, 4, 6, 8 electrons for that oxygen. That's going to be an AB, that's linear. Anytime you have only 2 atoms, it's going to be linear. You have no other shape options. For the nitrogen, if we do nitrogen, and the one thing I will say that I saw, a little bit of confusion, you don't always have to put the unshared pair on top. In this case, I would put the pair of electrons on the outsides like this, and then put your unpaired electrons facing each atom. You can see your first bond is going to be there. You have another pair that you can connect here, and a third pair that you can connect there. That's a triple bond. Again, AB is going to give you linear. And then, if we go down to carbon dioxide, where you have 4 electrons from the carbon and 6 apiece, 12 electrons from the oxygen, 16 electrons total, you have your carbon with its 4 electrons, 1 oxygen over here, and another oxygen over here. And hopefully we can see those bonding sites again. There's a bond there. There's a bond that's connected. We have another pair that we can connect here for a double. We have another pair here that we can connect for a double. 2, 4, 6, 8 around the oxygen. 2, 4, 6, 8 around the carbon. 2, 4, 6, 8 around the oxygen. That would give you AB2, A, B2. That's going to be linear. And why it's linear is because those double bonds make the bond angle between our carbon and our oxygens. Sorry, I have this on the wrong way here. The black is our carbon, the red is our oxygen. And you can see that the double bonds create a straight line, 180-degree bond angle. Now, last page here had the polyatomic ions. The thing to remember with your polyatomic ions is what the charge does to the number of electrons. Okay? So if we look at hydroxide OH minus 1, the -1 adds 1 electron. The CH3CO2 minus 1 adds the 1 electron. The BrO3 -1 adds the 1 electron. The C2H2, no charge, we'll come back to that in a second. The C2O4 minus 2 is going to add 2 electrons to our total. All right, so polyatomic ions are groups of atoms that are covalently bonded, but they only exist if they can gain or lose the extra electrons that are needed. With 8 electrons, oxygen and hydrogen are going to single bond. Hydrogen's good with just the pair, because hydrogen, if you remember its electron configuration, is 1s1. It has 1 orbital with a single electron. All that hydrogen wants to become stable is another electron to come in. If it can fill that 1s, it becomes like helium. So we get that 1 bond to hydrogen, we're good. We have AB, it's linear, you would draw it this way, and then that sets us up to start adding in electronegativities to do polarity. If you have a molecule like this, where you have 2 carbons, bond the carbons together first. After the carbons are bonded together, this is telling you that you have a CH3 group, CH3 connected to a CO2 group, CO2. So bond your carbons together and then put these atoms around that carbon, these atoms around that carbon. All right? And then you end up with your structure. Okay, you're going to need a double bond because you're going to run out of electrons. So the only way that you can make this with 24 electrons is to share 2 pairs instead of lone pairs and singles. The other thing is, whenever you have a polyatomic, you have to put it in brackets with the charge outside when you do the Lewis dot structure. You have to put the Lewis dot structure in brackets with the charge outside so that we know that only exists because that extra electron has been added in. The last thing I want to go through with you real quick is this Lewis dot, or the VSEPR. So the first carbon is A123 AB4. This carbon is A123 AB3. So this carbon right here is going to be a tetrahedral. So draw your tetrahedral. This carbon is going to be a triangular planar. Add the triangular planar onto it.